Hello. In this problem, we're asked to find the thermal efficiency, the net power output, and the backwork ratio of an ideal gas turbine operating under the Brayton cycle. And also, we have a what-if scenario. And what would be the efficiency if the compressor pressure ratio now is changed to 15 and the mass flow rate to 10 kilograms per second. So in this problem, we're going to use the ideal Brayton cycle. Pressure 1 is given as 101 kPa. Temperature 1 is given as 295 Kelvin. Mass flow rate is given as 6 kilograms per second. Now state 2 is after the compression, and this is considered an isentropic compression, which means the entropy at state 2 is the same as the entropy in state 1. The pressure is given that it's compressor pressure ratio of 8. So 8 times pressure in the first state. Mass flow rate remains the same as state 1. Temperature 2, we can solve for it using the isentropic relationship. T2 over T1 is equal to P2 over P1 to the power of K minus 1 over K, where K is equal to 1.4 for air. When we plug in our numbers, temperature 2 is 534.4 Kelvin. In state 3, this is after the combustion chamber, and this is considered constant pressure heat addition. Therefore, pressure 3 at state 3 is equal to the pressure at state 2. Temperature at state 3 is given in the turbine inlet at 1200 Kelvin. So 12. And mass flow rate remains the same, m.1. And in state 4 is after the turbine, which is after the isentropic expansion, which means the entropy at state 4 is equal to the entropy at state 3. And the pressure is, this is after the constant pressure heat rejection. Therefore, the pressure is equal to P1. Mass flow rate also remains the same. And once again, since it's an isentropic expansion, we can use the isentropic relationship, this one, to solve for T4. And when we do that, we get 662.5 Kelvin. Now with these 4 states ready, we can solve for the power in the compressor, which is mass flow rate times the change in specific enthalpy, which can be simplified to mass flow rate times specific heat times the change in temperature, given that Cp is 1.005. When we plug in our numbers, compressor power is 1443.6 kilowatts. The heat added is, once again, mass flow rate times specific heat times the change in temperature, which gives us And power in the turbine, after plugging in our numbers, it gives us 3241.1 kilowatts. And the heat rejected is mass flow rate times specific heat times change in temperature for the state 4 and state 1, which gives us 2216 kilowatts. Now with these numbers, we can solve for the net power output, which is 1795.5 kilowatts. The thermal efficiency is power output divided by heat added, which is 44.7%. And the backwork ratio is the power in the compressor divided by the power in the turbine, which is 0.445. Now we can solve this problem using the test app from thermofluids.net, and I'd like to thank Professor Bhattacharjee for providing this website. These are the properties that were given in state 1, state 2, state 3, state 4. Now we look at graphics panel, we can see the TS diagram, and device panel has been updated as well. Therefore, in cycle panel, now we have the net power output, which is 1795, which is the same thing as that. Thermal efficiency 44.8, 44.7, and backwork ratio is 0.445, 0.445. Now when we consider the what if scenario, in state 1, mass flow rate changes to 10 kilograms per second, and in state 2, the compressor pressure ratio changes to 15. Now we can check how that affects thermal efficiency, which now we can see that it increases to roughly 54%.